So folks, in this problem, we want to graph a function f that turns on the number 2 at time t equals 0, and then turns off the number 2 at time t equals 3. Then we'll explicitly write out that f, and I should say as a step function. So in this case, the graph of this function would look something like so. We want it to read a 0 until we get to time t equals 0, in which case it'll be turned on, and it will and we want it to actually display the value 2, which is different from before, and then we want to turn it off at the value time t equals 3 so that it continues to return a 0 from 3 on. So the first thing we could do is we could write this as a piecewise function, and this is nothing new. This is stuff that you've been doing for many years. We could say f of t, these are usually with t as our independent variable, f of t would be equal to 2 if 0 is less than or equal to t, which is less than 3, and 0 otherwise. I mean, there it is as a piecewise function. What we'd like to do, though, is we'd like to represent this as a unit step function. So better, and for the purposes of doing our Laplace transforms, we want to represent f of t in terms of this unit step function. So our f of t is going to be, so let's just think about this for just a second here. If we do step, and although we don't usually emphasize this, I'm going to write step t minus 0. So this is the function. If you remember how this function behaves, it turns on the number 1 at t equals 0 and keeps it on. So this will display this will broadcast the number 1. It's broadcasting 0 until we get to 0, and then it broadcasts the number 1. It would look like so. So just like the graph that you drew above here. But I wanted to display 2 times that, so I'm just going to double that. So we're using the new Microsoft OneNote, which is new and improved, and it doesn't work as well as the old. So now what we want to do is to make sure that the function gets turned off when we arrive at time t equals 3. So one way to think of that is something's happening at t equals 3. That's going to turn on that switch. And then what do we want to happen when we get to time t equals 3? When we get to time t equals 3, we want to somehow counteract this positive 2 right here. So in fact, what we'll do is we'll put a minus 2 right here. So let's just check this. This function gets turned on when we get to time t equals 0. The step function begins broadcasting a 1, but we double that output, so we're broadcasting actually a 2, and that broadcast actually stays on forever. But then what we want to do is when we get to time t equals 3, we want to turn on this function, which actually broadcasts, this function down here, which would broadcast a negative 2. So you could see that although this gets turned up, this gets counterbalanced down here, this is still as if it's broadcasting the number 2. But then when we get to time t equals 3, this is broadcasting a negative 2. And if I add together the 2 green terms, they combine to give me a 0, so that's the net effect of broadcasting a 0 after we get to time t equals 3. Folks, these step functions are at first a little bit confusing. If you're feeling overwhelmed, don't worry about it. You'll feel better as you get more comfortable. One of the most important tricks I have for getting comfortable with a step function is to just plug in different values into it. So let's go ahead and look at, for example, let's look at f of negative 1. That's going to be 2 times the step of negative 1 minus 0 minus 2 times the step of negative 1 minus 3. So that cleans up to be 2 step negative 1 minus 2 step negative 4. But how do these step functions work? The step function broadcasts the number 1 if the argument is greater than 0, greater than or equal to 0, and it broadcasts the number 0 otherwise. So in fact, both of these step functions evaluate to be, sorry folks, Microsoft has changed the way OneNote works, and it's not better. So both of these are broadcasting a 0 now, and so we get 2 times 0 minus 2 times 0, or it broadcasts a 0. That's what we'd expect when time is 0. Now let's check f of 1. So if we were to turn it on 1 here, this is going to go a little faster here. This would be 2 times the step, and we're going to plug in 1 into this function, so that's 1 minus 0, minus 2 times the step of 1 minus 3. But now, this step function broadcasts a 1 because the argument of the step function is positive, or non-negative, I guess I should say. And this step function here is still broadcasting the number 0. So when I plug in 1, the net effect is to have 2 times 1 minus 2 times 0. So it's broadcasting the number 2. So at time t equals 1, it does indeed output the value of 2. Okay. The last thing to check, and I'm sorry I've run out of room, is to let's plug in the value f of 4. So we plug 4 into this function. We get 2 times the step of 4 minus 0, minus 2 times the step of 4 minus 3. But look at how these two terms evaluate. This step function has a non-negative argument. Its argument is greater than or equal to 0, and so it's going to broadcast a 1. But same with this step function here. This would be the step of 1, and that also broadcasts the number 1. And so what we're left with is 2 times 1 minus 2 times, minus 2 times 1, which gives us 0. So at time t equals 4, even though the first step function is turned on, the second function is now also turned on, and we've had it broadcasting a negative 2, so they counteract one another, and we're back to a value of 0. Okay, let's try that again. So down here, what we have is what sometimes called, our textbook calls it, the Boxcar function. Okay. So the first thing to notice is that this is only going to apply, we're going to only have t values that are greater than 0. This is for t greater than or equal to 0. And what we want to make sure this function does is it broadcasts a 0 until we get to time t equals 1. So we're going to have step t minus 1. Notice that when time values, we can only plug in non-negative time values into this problem, because notice, and they could have just as easily had this graph continue on in the negative direction, but and you would just strike that piece. But we want to make sure that we don't start broadcasting anything. It's undefined until we get to time t equals 0. But if I plug in 0, we want to make sure that it spits out a range value of 0 in the step function. And for all domain values between 0 and 1, we want to make sure it's spitting out 0, and so we use step t minus 1. This then turns on the number 1 when we get to time t equals 1, and now we want to turn it off when we get to time t equals 2, and so we would just have minus, and just to emphasize this, let me put a 1 here just to emphasize that we're broadcasting the number 1, and then we're going to subtract that off for time values that are bigger than or equal to 2. So what I'd like you to do is just confirm, go ahead and compute b of, I guess you could say b of negative 1 is undefined. But then I'll have you find b of 1/2, b of 3/2, and b of 5/2. And compute each one of these the same way I did above, and convince yourself that the points are what they are supposed to be when you actually plug them into the step function. So actually practice that out. So I want you to go ahead and fill those out here. On the next page, I want you to take a shot, explain how the previous function works, think about it in terms of turning on, turning off, or come up with a narrative that works for you to explain how these switches work. And then I'll let you try number 7 on your own. So you'll want to pause the video. What I want you to do is evaluate these 3 remaining points, give a quick explanation of what we've just done, and then I'd like you to come up with your own boxcar function. Everything's just slightly different here. We broadcast the number A, we've got A's here, etc. So pause the video and work through, I guess, all the way through question 8. So lastly, folks, I want to look at kind of where we're going with this. You may be thinking, okay, this helps me display dashes as signals in terms of these unit step functions. What about more complicated functions? So I just want to show you where we're going to go, and we'll practice this in class. For now, what I'd like to do is to create this function, g of t, right here. And you can see the g of t sometimes is displaying aspects of our ordinary sine curve, and other times it's just displaying 0. So I think of it as sending out these pulses at various increments of time. This does just continue on forever this way, and I do have set it up so that this is working for time between minus infinity and infinity. So let's try this out here, folks. The first thing I'm going to do is we want to make sure that we start at time t equals 0, we start broadcasting our sine function. So let's just turn that on. So how are we going to do that? Well, this would turn on the step function, step, and you could just write step t. I'm perfectly fine with that. I'm going to write step t minus 0 as we're just getting used to this. This starts broadcasting a 1 for time values greater than or equal to 0, and I'm going to multiply that 1 to my sine of t function. So notice that when this displays a 0 times sine of t, it just outputs 0. But when t is greater than or equal to 0, the step function is outputting a 1. Multiplying that to the sine of t turns it on. So what we've got here is then a function that starts at time t equals 0, and it would look like this. The problem is that I don't want it to always be displaying the sine function. So we're going to turn off the sine function when we get to time t equals pi. There's a couple ways to think about that. What I'm going to think about here is I'm going to say we're going to take minus sine of t, step t minus pi. So again, this green contribution is going to do nothing for time values less than pi. It's contributing 0. Then I'm going to think about this as the function minus sine of t, because of the minus sign there. And so when we get to time t equals pi, this function is going to turn on, but the function minus sine of t that I'm showing here in green looks like so. And you can see that what we have here is that this green function is starting at, for time values greater than or equal to pi, it's exactly counterbalancing my sine function, giving us a flat line of 0 all the way across. Okay, so now I want to, that works, that gets us started, but now I want to, by the time I get to time t equals 2 pi, I want to start displaying that sine function again. So let's do that. So when I get to time t equals 2 pi, I want to add in a sine function. So this function now turns on here at time t equals 2 pi. And although I've got now several functions being displayed, so for these time values, for instance, I'm broadcasting both the red sine function, the green minus sine function, and the yellow sine function. The green and red are counterbalancing each other, so the only one showing is the red sine function. Finally, we're going to turn that off. When we get to 3 pi. So when I get to time t equals 3 pi, I'm going to again display the minus sine function, but now I'm going to keep that one on for the rest of the time. And so for time values in between 3 pi and infinity, the green function is always counterbalancing the red function, and the purple function is always counterbalancing the yellow function, so it is just displaying 0 all the way across. Folks, this takes a little while to get used to. I think eventually you'll find that it's actually pretty natural, but I certainly understand if you're feeling a little intimidated by these step functions right now. This pre-work was just to get us ready for them, and then we're going to start studying them in more detail in class. Thank you very much.